Hello everyone, welcome to the PSpice tutorials. In this session, I will demonstrate the VI characteristics of the Zener Diode using the OrCAD PSpice student version tool. Please note that I will not be discussing the theoretical aspects of the Zener Diode in this session. I have already made a video on that and I would suggest you to kindly refer to the same for more information on Zener Diode. I will leave the link of that video in the description below as well as at the end of this session. Before I begin the simulation, I would like to mention some of the important characteristics of the Zener diode. At first, it behaves very similar to a normal signal diode under the forward biased conditions. However, Zener diodes are more commonly used in a reverse bias condition. Under reverse bias conditions, it behaves considerably different than a normal diode. That means, in reverse bias condition, Zener diode withstands a applied reverse voltage only up to a certain value called as the Zener breakdown voltage, below which the diode breaks down due to the Zener breakdown effect. This is different from the avalanche breakdown and occurs at a lesser value than what a normal diode would experience the avalanche breakdown. That means that theoretically, Zener breakdown occurs at a lower voltage level than the avalanche breakdown in a diode that is especially doped for Zener breakdown. Now let us look at the characteristics. When a Zener diode is connected across a voltage source and the source voltage is more than the Zener voltage, the voltage across a Zener diode remains fixed irrespective of the source voltage. Although at that condition, current through the diode can be of any value depending on the load connected with the diode. The VI characteristic curves of the diode, Zener diode, are as shown in the diagram here. We expect to obtain a similar looking curve from the simulation experiment. Please note that I will be using the DC sweep analysis to obtain the characteristic curves. However, you should know that it is also possible to obtain the same using time domain analysis. For more information on this, refer to the video named Diode VI Characteristics using Time Domain Analysis in my channel. I will leave the link of this video in the description below as well. Right, let us start with the simulation part. Remember, for simulation, I will be using the student version of the OrCAD PSpice version 9.1 software, which is freely downloadable. Right, so I will start the simulation part first by starting and searching for the Capture Student, which is the application you should launch to obtain the simulation. Right, so I'm going to create a new file here, going to a new project, create project. You will have multiple options available under the project type. Select analog or mixed AD. Here I will name the project as Zener Diode. And if you want to save it at a certain location, you can do the same. I'm going to my desktop. I'm going to create a directory. I will name it as Zener Diode Characteristics. This is my project name. Press OK and press OK here. Make sure that has properly appeared on the link here, which is the location of your project here. So I'm going to click OK here. Now I'll be asked if I want to create a project based upon an existing project, which I don't want to do. So I'm going to create a blank project, press OK. Right, so this is what the simulation window would look like. Let us drag this down a little so that it can be very properly visible. Right, so now it is time to place parts. Okay, so you need to left click on the simulation screen to get this particular menu option, which is place. So go to place, select part. You can do the same by simply pressing the P button or P key from your keyboard. Right, so let me start by first and foremost identifying the Zener diode. In the student version, it is given as D1N750. Okay, so select by double clicking the same and place wherever you want it to. So I'll just place it here. Okay, so let me just zoom in a little so that it is a little clearly visible. Right, so this is my Zener diode. Along with that, I would definitely require some DC voltage. So go for part by pressing P from your keyboard. Search for VDC. right? So select VDC source and place it here. Then I would go once again to the parts. I'll select a resistor here. Simply press R. Select R analog. It is horizontal. So press R from the keyboard. So it will become vertical. That is, you can use that to rotate the part of any particular device you have or part you have. You can rotate it by simply pressing R. So this is enough for me. So I'll place it here. And you usually should note when you select a part, it is usually attached to the cursor. So if you want that to go away, simply press escape button. Right, so now my circuit is almost okay. I would like to now connect these components by wiring. So for wiring, you can either select this icon at the right side menu here, or you can simply press W. Right, so if you just look at this, when I press W from my keyboard, the cursor changes from the arrow to a plus sign. So go to the parts, select them carefully, make sure they are properly connected. Otherwise, you are going to have some difficulty in identifying the connection mistake. Right, so this is about my connection. I still need to place a ground. So once again, go here and select the ground, or you can do the same by simply pressing G from your keyboard. So I will select 0 source, place it here. Once again, I need to connect the ground with the circuit. Press W and select the component and connect it to the ground. Right, so this is done. Now I'm going to have a DC voltage. I'll simply, for the namesake, give it as 5 volts DC. Okay, right. So press OK. So please make sure your name of the diodes and components are known. This is voltage source V1, diode D1, and this is resistor R1. I'll keep it at 1K. That is completely okay with me. Right, so this is about the circuit. This is a very simple circuit at that. So to run the simulation, I need to create a simulation profile. Now to do that, go to the menu, select PSpice, select new simulation profile. Okay, now you can give the simulation profile. You can give whatever you want. So I will simply give Zener simulation profile. Okay, I don't want to inherit it from anything else. So simply click on the create button. So now identify there is a new pop-up window appearing. Select that. As I already have said, I am going to select the DC sweep analysis. Okay, so now you have so many components available here. Select the primary sweep. By default, it is selected. Select the voltage source and select the voltage source you want to sweep. Obviously, I have only one voltage source here, which is V1. Name it as V1. Okay, right. So I want to sweep it from, let us say, I'll only first and foremost illustrate the fault characteristic curves. I'll start from 0 and the end value, let it be 5 volts. And I would like to increment it in terms of 0.1 volt. Okay, right, apply. Okay, simulation profile is ready. Now you can click on the simulation run spice button here, which you will find again in the PSpice menu. So let us run that and look out once again at the pop-up window here. Right, so this is what your simulation profile simulation window would look like. But what I would now do is I'll simply place a current marker. This is the current marker here. Select that and connect it exactly at the anode edge. Okay. Right, so with that I will once again run the simulation and I note that the forward characteristic curve has already appeared. This is a very similar one to that of a normal signal diode, as we already have said. Okay, so it is breaking somewhere around 0.7 volts. Right, so this is about the forward characteristics curve. If I want to perform the reverse biased condition as well, I simply would go to the simulation here, just select the edit profile. Now I want to run the simulation for negative voltages. So you can start your start value. You can select your start value to be a little different. So let us say I'll see minus 3 volts. Okay, apply, press OK, run the simulation. Now the x-axis varies between minus 3 to plus 5 according to the range I have given. And I note that the Zener diode has not broken. Right, so no breakdown effect here. That means that the reverse voltage applied is not sufficient enough. So once again, go to the simulation profile, edit. Now make it, let us say, minus 5. Okay, apply, press OK, run the simulation again. Right, so now you can see at around 3.5, the diode has started to break down. However, the reverse current is not sufficient enough. So in order to make it more clearly visible, I'll change the voltage from minus 5 to, let us say, minus 10. Okay, so higher value is 5 and incremented in terms of 0.1 again. Apply, press OK, run the simulation again, and now you can see the breakdown is properly visible. So this is how you obtain the VI characteristic curves for a Zener diode. If you want a very properly looking simulation output, simply change the start value to minus 50. So you can now look at the current waveform across the reverse bias condition, right? So it is pretty neat in this particular waveform. Okay, so x-axis is our voltage applied, y-axis is the diode current. So, and the breakdown appears somewhere around, this is about 5 volts, right? So now what I will do is, you can compare this diode characteristics with a simple or a normal signal diode. Okay, right. So in order to do that, I'll just modify my circuit. So what I'm going to do is, I'm going to create another circuit, but with the same supply voltage applied. So go to parts, select D1N 4002. This is my normal diode. So now 4002 is selected. Let me place it here. So what I would do, I'll simply rotate it and I'll place it here. Okay. Now I want another resistor. So once again, go to parts, resistor. R analog should be selected, and rotate it and keep it here. And I want wires now, so press W. So connect the diode to the same supply what you have here. Right, so this is my connection. Once again, I'm going to place another ground to this. Zero source is selected, and I'll connect it to the circuit as well. Right, so this is completely fine. Let us just move these components a little bit so that it looks okay. Right, so now please note, we have two diodes. One is the normal diode D2, another one is the Zener diode D1, and the resistors are R1 and R2 respectively. Anyhow, the ground remains the same. Right, so let us place another current marker across the anode of D2, so that we will plot both the currents for Zener as well as the normal diode. And let me just go to the simulation profile and illustrate the forward bias condition. So I'm going to remove this minus 50 and place 0. So I'll now be varying between 0 to 5, and I'll increment it by 0.1. Please note that you should have the same input voltage, and that is very essential. Okay, so you cannot have two different voltage sources and run the simulation. That is not possible. So same voltage source and connected in a certain fashion. Right, so I'll save it and run it. Right, so now you can look, the characteristic curves are as shown in the diagram here. And as I already have said, the forward characteristics of the Zener are very similar to that of a normal diode, and it is pretty clearly visible in this particular simulation result. In order to understand the reverse bias characteristic curves, you simply go to simulation and edit the profile. Now I will vary from let us say minus 10, and I already know that Zener is breaking at minus 5. Now I would like to know whether the normal diode would also break at minus 10 voltage. Now yes, so we have now two curves. The red one represents that of diode D2, and if you come back and look at the circuit, diode D2 is my normal diode and D1 is the Zener. So Zener is breaking down somewhere around 5 volts. However, the normal diode for D1N 4002, it is actually not breaking at all. The difference is the normal diode experiences avalanche breakdown, whereas the Zener experiences a Zener breakdown, and hence the name obviously. So in order to understand at what voltage this would break, and in fact if you remember, I have already simulated this in one of my previous videos. I will go to a little higher voltage. I will go to minus 120 because the normal diode breaks down at around 100 volts. So I have changed the voltage to minus 120 to 10, and let's run the simulation now. Yes, you can now very clearly see the Zener breaks down the green color curve at around minus 5 itself, whereas the normal diode breaks down at around 100 volts. So what I will do is I'll just change the y-axis settings. So in order to do that, I go to plot axis settings. Sorry, I need to remove the added axis now. So go to plot axis settings, change the y-axis, select the y-axis first, change the range and select it from something around let us say 20 milliamperes to 120 milliamperes. So I'll change it as 20 milli to I want the forward to be, yeah, this is 120, this is supposed to be 20, right? Apply OK, and yes, now you can very clearly see the reverse characteristic curves, right? So this is how in fact you are going to simulate and compare the VA characteristics of a Zener diode with that of a normal signal diode. Okay. Yeah, if you want to export these plots and all, you need to first and foremost remove the grid because it's not going to be of much help. So go to plot, select, let me just show you once again. Go to plot, select axis settings, select the X grid. The left one is for the major lines, which is the continuous lines I can see here. And the right column is for the discontinuous lines, the minor grid. So remove the minor grid for both X and Y. Press OK. Yeah, now you can see there is a lot of difference. If you want, you can in fact change the color of the curve also. So select the curve of interest and right click, go to properties. You can change here, right, to whichever color you want. Press OK and it will automatically change. Right? Yes, so this is how you would obtain the VA characteristic curves of a Zener diode. And in fact, in this particular session, I have compared the characteristics of the Zener diode with that of a normal signal diode. Right, so that is all about this particular session, and I hope that you found this session informative. Thank you for watching. Have a good day.